So today we will do the next topic in the chi-square distribution. So before coming to that theorems, first of all we will learn about the linear transformation. We are doing the chi-square distribution. So under this, first of all, now we will read linear transformation. So what is the meaning of linear transformation? Suppose we have a set of variables x dash having the values x1, x2, so on up to xn, and it is transformed into a new set of variables y dash having the values y1, y2, so on up to yn by means of linear transformation. By means of linear transformation, right? So how it will be written? Y1 is equal to A11x1 plus A12x2, right? Then this is written as A11x1, A12x2, then plus so on up to A1nxn. Then what will be y2? y2 is A21x1 plus A22x2, so on up to A2nxn. So in general, what will be yn? This is an1x1, an2x2, so on up to annxn. So this is x is transformed into the variable y by the linear transformation, because we have here the power 1. Y is the linear combination of the vectors. In other words, we can say x1, x2, so on up to xn. So in general, what is yi? Yi is yi1, x1, i2, x2, so on up to in, xn, and I is running from 1 to n. So in matrix notation, how we will the linear combination of the linear system of linear equations that can be expressed as y is equal to ax, where y is a column matrix having the values y1, y2, so on up to yn. X is also here column matrix xn, and capital A is equal to, it is a coefficient matrix a11, 12, a21, 22, so on up to a2n, and this is an1, an2, so on up to ann. This is the coefficient matrix. Now from the matrix theory, we know that this system, the whole system number 1, this system has a unique solution. Number 1 has a unique solution if determinant of A is not equal to 0. If determinant of A is not equal to 0, right? That is, we can express x uniquely in terms of y. It implies we can express x uniquely in terms of y if the coefficient matrix is non-singular. So non-singular matrix means the determinant of the matrix is not equal to 0 and the solution is given by x is equal to A inverse y. Where A inverse is the inverse of the square matrix A, right? Now the next in the category is linear, is the transformation is orthogonal. When the linear transformation is called orthogonal. So next heading you will give orthogonal transformation, right? So linear transformation that we have defined like y is equal to x. This is a linear transformation. This is said to be orthogonal. Y is equal to ax. This is a linear transformation. This is said to be orthogonal. Which condition should be satisfied? X dash x is equal to y dash y. That is x dash here is nothing but the x dash. One is the x we have the column matrix, and x dash we have the row matrix. So x dash x is equal to, put the value of y here, this is ax dash into ax, right? Then what will we have? This is equal to x dash a dash a into x, and this is the identity matrix. It implies x dash x is equal to we have x dash x is equal to, so अब दोनों तरफ से देखो आपके पास क्या आ गया, वन एक साइड पे है x dash x, दूसरी साइड पे भी क्या है x dash x, इसका मतलब a dash a आपके पास क्या आ जाएगा, it implies a dash a, this will be the identity matrix of order n cross n, right? So the condition for the orthogonal transformation is that A must be a orthogonal matrix. Therefore, transformation, therefore linear transformation is orthogonal if the linear transformation is orthogonal if the matrix, the coefficient matrix A is orthogonal. If the coefficient matrix A is orthogonal, that is when A dash A is equal to IN. Okay, जी? We will elaborate it more. So more elaborately, what we will say, x dash x is equal to y dash y. So when you have like this, you have the variables x and here, and you have here. So one row vector is multiplied with the common vector. Same here. So what you will get? This is x1 square plus x2 square plus so on up to xn square. This is summation I running from 1 to n xi square. Similarly, here you will get summation yi square. Right? With the set of variables. So it implies summation I running from 1 to n xi square is equal to summation I running from 1 to n a I1 x1. We will put the value of yi here. A I2 x2 so on up to a in xn its whole square for every set of variables x1 x2 so on up to xn. Now, what is delta ij? Delta ij is known as the Kronecker delta, right? So, this is equal to summation k running from 1 to n. This is aik and akj for all I and j is equal to 1, 2, 3, so on up to n. Then, what is delta ij? It gives two values. This is giving 1 when I is equal to j and 0 when I is not equal to j. So when you will put the value when I is equal to j, जब I और j जो है वो same है, then it is the give value 1. Otherwise, it is the value it gives the value 0, right? So it implies. So what it does, it implies A is a orthogonal matrix. So either you can solve by this or you can do by this, right? Now, next definition is linear orthogonal matrix. Linear orthogonal matrix. So, linear transformation Y is said to be orthogonal if A is an orthogonal matrix, right? A linear transformation Y is equal to AX is said to be orthogonal if A is an orthogonal matrix. So when A is the orthogonal matrix, if A dash A is equal, yani A transpose of A into A is equal to A into A transpose is equal to IN. So a square matrix, linear orthogonal matrix, here A is the linear orthogonal matrix which satisfy this condition that A dash A is equal to A dash is equal to IN, right? So we can use this, either we can use this or we can use that summation of xi square is equal to summation of yi square, right? So we can use these two conditions as a matrix or a linear transformation is said to be orthogonal if how it is if xx dash is equal to x dash x is equal to y dash y, or we can say that a dash a is equal to a into a dash is equal to the identity matrix of order, right? So we will now use this whole concept in a theorem. So the name of the theorem is Fisher's lemma. So what the lemma says, if xi, हमारे पास xi वेरिएबल्स हैं, सारे नॉर्मली डिस्ट्रीब्यूटेड हैं with mean 0 and variance sigma square, right? They all are independent. Second thing is they all are independent, right? And how many? I is equal to 1 to 3, so on up to n. And they are transformed to a new set of variables. They are transformed in a new set of variables, so yi, right? And having the values I, 1, 2, 3, so on up to n. Kaise? By means of linear transformation. By means of linear transformation. ठीक है जी? Then yi I is equal to 1 to 3 so on up to n are also prove क्या करना है और also independent normal variates with mean 0 and variance sigma square. So what is given? We have given x's are independent normal variates with mean 0 and variance sigma square. They are transformed by the linear transformation and having a new set of variables y1. Now we want to prove that yi, all the yi variables are also independently normal distributed variables. Let's come to its proof. Proof of Fisher's lemma. So from where we will start? As a transformation, we know that let the linear orthogonal transformation be let the linear orthogonal transformation be y is equal to ax such that y dash y is equal to x dash x and a dash a is equal to in. So जो हमने पीछे एक बेस बनाया linear transformation का orthogonal का, that we will use. Now since each xi follows n0 sigma square, right? For all I running from 1 to 3 so on up to n. Then the joint PDF of all xi is given by f of x1, x2, so on up to xn. अब सारे variables क्या हैं? Independent है. So joint is equal to product of their marginals. So हम यहाँ पे marginal लिखेंगे f of x1, f of x2, so on up to f of xn. So now we will substitute the PDF of the normal distribution 1 by sigma under root 2 pi, right? Because they have the common sigma e raised to power minus क्या होता है x minus mu लिखते हैं यहाँ x1 mu is 0 minus 2 sigma square into 1 by sigma under root 2 pi e raised to power minus x2 by 2 sigma square, so on up to 1 by sigma under root 2 pi e raised to power minus xn upon 2 sigma square. So 1 by sigma under root 2 pi. How many times? N times. E raised to power minus 1 by 2 sigma square. This is x1 plus x2 so on up to xn. ये हमने sum up कर दिया. ठीक है जी? This is whole square. X minus mu whole square होता है. So you will get here square. x1 square, x2 square, xn square. This is 1 by sigma under root 2 pi whole raised to power n. This is e raised to power minus 1 by 2 sigma square. This is summation I running from 1 to n xi square. Right? And definitely all the values x1 joint जो है, it is lying between minus infinity to infinity. Right? Now, in order to convert, अब ये आपको पता है इसका expression है x dash x. So you will write here, this is 1 by sigma under root 2 pi raised to power n e raised to power minus 1 by 2 sigma square into x dash x. So this is the question of transformed variables. We have already done the procedure how to find the PDF of the transformed variables. Now we will transform we have the transformation of the variables in terms of y. So in order to find the PDF of y, we have to find the Jacobian of transformation. So now the joint PDF of y1, y2, so on up to yn is given by, that was f, here we will take y, g1, y2, so on up to yn. So this is 1 by sigma under root 2 pi n. So you will convert all xi's in terms of yi's. So you have the formula summation of xi square is equal to summation of yi square, or x dash x is equal to y dash y. So this is minus 1 by 2 sigma square. You will write here y dash y into Jacobian of transformation. Where first of all we निकालेंगे 1 by j. 1 by j हम इसका reciprocal हो जाएगा y1 y2, because you have given y in terms of x. It's quite bit difficult to convert x in terms of y here. So we will use the reciprocal. So when you will what does it mean? It means curly y1 by curly x1, curly y1 by curly y2 by curly x1. इस तरह से ये आपके पास एक डिटर्मिनेंट आ जाएगा. Here curly y1 y2, यहाँ सारे y1 ले लीजिए, curly x1, so on up to curly yn by curly x1, और लास्ट में आपका जाएगा curly yn by curly xn, राइट. और यहाँ पे आपका जाएगा curly yn by y1 y2 y3, यहाँ y1 है, सारे y1 है, y2 y3, so on up to yn. Then this is curly x1, curly x1, curly x1. So this comes out to be, ये जो आपके पास डिटर्मिनेंट पूरा बनेगा, I'm writing on the next page. So curly y1 y2, so on up to yn upon curly x1 x2, so on up to xn is equal to 1 by j. We are finding this is curly y1, curly y1, curly y2, curly y3, so on up to curly yn. So this is curly y1 by curly x1, curly y1 by curly x2, so on up to curly y1 by curly xn. This is again curly x1, curly y2 by curly x2, so on up to curly y2 by curly xn, curly y3 by curly x1, curly y3 by curly x2, curly y3 by curly xn, curly y1 by curly x1, curly y1 by curly x2, and the last will be curly y1 by curly xn. So ये एक determinant बनेगा, and then you will find out what you will get. You will get the mod of it. आप जब इसको solve करेंगे, you will get the, because what transformation you have given, y is equal to ax. So here we have mod of it. Now it is orthogonal matrix, so a dash a is equal to in. It implies a dash a, its determinant is equal to in, and the determinant of in, that will be 1. So this is a dash a into a mod into 1, right? So here, what is the transpose of A's determinant? That will be same, mod of A into mod of A is equal to 1. That is mod of A square is equal to 1. ठीक है जी? That is mod of A is equal to plus minus 1. As J is equal to 1 by J is equal to mod of A. It implies J is equal to 1 by mod of A. It implies J is equal to 1 upon plus minus 1. And what is mod of J? That is equal to 1. So we will substitute in the Jacobian of transformation. So we have G of y1, y2, so on up to yn is equal to 1 by sigma under root 2 pi raised to power n e raised to power minus 1 by 2 sigma square y dash y into 1, right? So what does it mean? This is 1 by sigma under root 2 pi raised to power n into minus 1 by 2 sigma square. This is y1 square plus y2 square, so on up to yn square. Separate कर दीजिए. So this is 1 by sigma under root 2 pi e raised to power minus 1 by 2 sigma square y1 square. 1 by sigma under root 2 pi e raised to power minus 2 sigma square y2 square. 1 by sigma under root 2 pi. यही n को हमने सबके साथ split कर दिया. e raised to power minus 1 by 2 sigma square into yn square. So it means the joint, this is the g of y1 into g of y2 into g of yn. So the joint PDF is converted into the product of marginal. It implies each yi is independent for all I1 to 3 so on up to n. And yi follows non but distribution mean कितना आ रहा है इसमें? ये 0 है. You can write over here minus 0 whole square. You can write like that. So 0 sigma square, right? So this is the one of the theorem based on linear orthogonal transformation.